All right, so let's start by covering acid anhydrides. There's a couple different ways to prepare acid anhydrides, and I'll show you both of them. The first one is for really, really simple acid anhydrides. You can just take acetic acid, crank up the heat to 800 degrees Celsius, and you can form acetic anhydride. However, you can imagine if you're running any sort of normal reaction, 800 degrees Celsius is not at all practical, right? So this only works for making really simple anhydrides. If you want to make a more complicated anhydride, what do you think an approach could be? What's more reactive than an anhydride? Acid halide, right? So let's say we take an acid halide and we want to make acetic anhydride. What would we need to react it with? What do you guys think? Yeah, carboxylate salt, right? So in this case, you can take just a normal carboxylate salt, where you've got a negative charge, and you can convert this, you can convert this into an acid anhydride. This is usually the preferred method for making acid anhydrides because it's much more gentle than 800 degrees Celsius. 800 degrees Celsius will cook most of your reactions. Let's briefly do the mechanism for this. The mechanism's very straightforward. I'll just use a generic R group. Your carboxylate anion will attack into your acid halide, kick up electrons. Oops. Let me clean this up a little bit. R prime. And then this oxygen can clamp down, kick off the chlorine. Oops. And you'll get to your acid anhydride product. And let's put in this chlorine right here too. Why do you think this reaction goes left to right rather than right to left? Why don't we have chlorine come, why don't we have the chlorine come and attack in and go in that reverse direction? Yeah, the chloride's a really, really stable leaving group. So in this case, it's really a battle of nucleophiles. You can think of this as an equilibrium reaction. But the chloride's so stable as a leaving group, you're going to favor the formation of your acid anhydride. So let's look at a few practical examples from the textbook. So common here, let's change it. Used often for acylation. And I'll show you guys what I mean. This is a classic example. Does anybody remember the name of this compound where we have one carboxylic acid on top and an alcohol over here? This was from the azodye lab. Anybody? Another hint is it's in face wash and will bleach your towels if you dry your face with it afterwards. Yeah, salicylic acid. So salicylic acid, if we treat it with acetic anhydride, what will it form? Let's try to predict the product. Do you think that this oxygen is going to be a very good nucleophile? No. So it's probably going to be the phenolic position that acts as the nucleophile. It can add into our acid anhydride, and then our final product that we get out will have this acyl group coming off of it. And so you can use this to convert salicylic acid into aspirin. Pretty slick reaction. It's often done in Gen Chem labs or in OChem labs. The next one that's common is where you try to acylate this starting material. But now the question is, what do you think is going to be more nucleophilic, the nitrogen or the oxygen? Nitrogen, right? If you guys remember our trends for nucleophilicity, we said that the more electronegative the atom is, the more tightly it's going to hold its lone pairs. Because nitrogen's less electronegative, that means it's going to be more nucleophilic, and we can acylate that nitrogen. And we can use this to make Tylenol. So you can use acid chlorides if you wanted, right? So you could use acetyl chloride for each of these reactions. However, this is a much more gentle way to acylate the nitrogen or oxygen positions on either of these. And in fact, if you try to use acid chloride for the Tylenol example, you might actually acylate both positions instead of just the nitrogen position. So this is typically the preferred route for acylations. All right, let's do a really brief reaction map again, just to kind of show the utility of this. I'm going to have you guys help me fill in the arrows. We'll have our carboxylic acid on the left. We'll have our anhydride in the middle. I'll put an ester on the top left, an amide on the top, another amide over here, another amide over here. We'll put a primary alcohol over here with two hydrogens. We'll put an aldehyde down here. We'll put a tertiary alcohol over here. I'll use R primes. And then last but not least, we'll put a ketone over here. So now we've got to try to connect all of these. So the first one is, how can we go from a carboxylic acid to an acid anhydride? What do you guys think? We could crank up the heat to 800 degrees, but then we might cook our product. Really what we need to add on is this group. How could we add on that group? What was that? We could use our acid halides, right? We said acid halides are far and away the most reactive electrophiles, so they'll react with the carboxylic acid. This would be a two-step process. First step, you'd need to deprotonate your carboxylic acid to make that oxygen right here a really good nucleophile. And then you'd want to react this with acyl chloride. So I'll write CH3COCl, and that would add on that acyl group. So you can convert your carboxylic acid to an acid anhydride pretty easily. What if you want to go backwards? Water, exactly. So you could hydrolyze your acid anhydride. We said the other route that can be used for really simple ones was just crank up the heat to 800 degrees Celsius, but that's not that useful. All right, how could we go from our anhydride to our ester? Let me try to move this over. What was that? Alcohol, right? So we saw yesterday you can throw in alcohol. Normally this is run in pyridine to soak up any of your acid that's formed, but you can convert this to an ester. And then for an amide, what would we need? Yeah, ammonia in excess. So it's going to act as the nucleophile and the base. It's the same thing for both of these, right? So we'd need RNH2 in excess for this one, and then R2NH in excess for this one. So you can make amides from these pretty easily. What do you think we need if we want to go to a primary alcohol? I'll give you guys a hint. We added in 2 hydrogens. LAH, exactly. So we need to overshoot our reduction. So we can use lithium aluminum hydride. And you need to use excess in this case, followed by weak acid. And then the question is, how could we stop at the aldehyde? Bulky hydride source, right? What was the bulky hydride source? Yeah. The lithium. So LiAlOR3H. So the lithium terbutoxy aluminum hydride, followed by generally a water workup. And then what about if we want to add on 2 alkyl groups? Grignards. We know Grignards will add uncontrollably, so we'll write R prime MgX in excess, followed by some sort of water workup. And what if we only want to add in 1 alkyl group instead of 2? What was the new reagent we covered? R2CuLi, the lithium dialkyl cuprate. Does anybody have an idea of why the lithium dialkyl cuprate doesn't add in multiple times? It doesn't feel like it. If atoms had emotions, we could argue that. Exactly. If we look at magnesium on the periodic table, it's in group 2A. The difference in electronegativity between magnesium and carbon is really, really big versus the difference in electronegativity between carbon and copper, right? So it's a much more gentle reagent, and it can also be used to alkylate and anhydride. All right, let's do one with esters. So we'll try to change gears. We're gradually going to less reactive compounds. Let me delete this. Why can't I delete this? Well, just 1 second. I gotta get my keyboard in here. The Dean Stark trap is in the way. See, there it goes. All right. So now let's move on to esters. And let's talk about how to prepare them first. Does anybody have an idea for how we could prepare an ester using chemistry we already know? We just covered one yesterday and a new one today. All right, guys. Come on. Help me out a little here. We can use acid chlorides. Right, so we saw in our reaction map yesterday, you can use an acid chloride. You can react this with your alcohol. Let me clean this up. And we said normally you run this in pyridine, and if you do this, you can create a new ester. We also saw that we can make esters from anhydrides today. So if you've got an anhydride, we said you could use alcohol and pyridine. What's another way we can make an ester? What's that? Yeah, Baeyer-Villiger oxidation. All right, let's throw that one down. So this was one we covered previously where we said if you've got a ketone or, well, I guess a ketone only in this case, you do RCO3H, you can convert this into an ester. And remember, we have to pay attention to which alkyl group on the ketone is more likely to migrate onto that oxygen. The next one is pretty darn simple. What if we want to convert a carboxylic acid into an ester? Let me move this down. How can we convert a carboxylic acid into an ester? Yeah, exactly. SN2 chemistry. So first thing we want to do is deprotonate our carboxylic acid and then use it as a nucleophile. We saw this a long time ago. However, that R group needs to be primary or a methyl group. It can't be secondary. Typically that reaction is just too sluggish. What about in lab? How did we convert your benzoic acid into an ester? Does anybody remember the name of that reaction? Yeah, Fischer Esterification, right? So Fischer Esterification. This was one we talked about a couple days ago, and we said we did this in lab. What reagents do we need in order to do a Fischer esterification? Alcohol and what else? Acid, right? So the main thing that we did in lab is you guys put in sulfuric acid, a bunch of methanol, and you refluxed it for a while. That was our Fischer esterification. This is honestly one of the easiest ways to make an ester and one of the cleanest ways with high atom economy. If you do want to review that mechanism, we covered it, I guess, 2 days ago. But it's a pretty simple mechanism. First step, we protonate the carbonyl, then the alcohol adds in, and then a bunch of proton transfers, and we kick off water as a leaving group. All right, now let's talk about chemistry involving esters. Whoop, come on. The first one is hydrolysis. So if we take an ester, let's just do a generic one, and we want to go to our carboxylic acid, I'm going to actually draw this as equilibrium arrows. We would need water, so I'll put water on here. And then we would need alcohol as our leaving group, right? So this is basically the reverse of forming an ester from a carboxylic acid. If you think about this in terms of our Fischer esterification, we said that these are typically done under acidic conditions. How could we get the reaction to favor going back to our carboxylic acid? What was that? Yeah, a bunch of water, right? So in lab, I told you guys try to use really clean, dry glassware. You wanted to have the most amount of methanol if you were trying to form your ester. But if you're going in the reverse direction, just flood it with water, right? So in this case, you can do acid catalyzed hydrolysis. However, you need to use a lot of water. To push the equilibrium. So that's one way to do it. There's also a second way. That's common in soap making. So if you think about most fats, they're actually triglycerides, right? So they actually are 3 ester groups with a glycerol backbone. Does anybody know what you use when you're soap making? Yeah, sodium hydroxide. So with saponification, you use sodium hydroxide. The hydroxide acts as your nucleophile, will kick off your alkoxide as a leaving group. And with soap making, you typically stop there. But what if we want to isolate our carboxylic acid? You just add acid in for the second step. So this is kind of a roundabout way to form a carboxylic acid, but it works. And this is called saponification. All right, the next one we're going to look at is for forming amides. Which I'm just going to put down here as terrible. But we're going to look at it anyways. Let's say we want to form our primary amine. Why do you think this reaction is terrible? We know ammonia is a pretty good nucleophile. That means that this must be a kind of mediocre electrophile. That means that this reaction is slow and not common. What would we do if we had an ester and we wanted to get to our amide? What might be a better route?
Is it slow because the other oxygen being right there?
It's slow just because that carbon on your carbonyl is just not very electrophilic. If you think about your leaving group coming off here, it's an alkoxide leaving group. That's not a very good leaving group, right?
Yeah.
We said the pKa of an alcohol is about 15. That means an alkoxide is not going to jump off very easily. So this is really slow. It's not common, but what's a workaround we could use if we want to truly go from our ester to our amide? Yeah, convert it to a carboxylic acid, and then what could we do? Then we can maybe turn our carboxylic acid into an acid halide using thionyl chloride, and then do our addition of ammonia. So you actually have to use some more workarounds if you truly want to form an amide from an ester. That's kind of the limit to the utility in terms of nucleophilic acyl substitution, but there are some reductions that work well. So let's say we want to reduce our ester and go to a primary alcohol. What's our most commonly used reagent? What was it? Yeah, LAH, lithium aluminum hydride. We use this in excess followed by water. We've seen this plenty of times already. However, what if we want to go from an ester to an aldehyde? What do you guys think a solution might be? Yeah, so we might want to use a bulky hydride source. And in this case, we actually don't use lithium terbutoxy aluminum hydride. That doesn't work well for esters. We have to use a new reagent. And this new reagent that's very similar is called dibal. So DIBAL. And sometimes you see it -H or dibal H. And then we quench this with water. So let's take a look at what dibal actually looks like. Why do you think it's called dibal? What do we call these groups? Isobutyls, right? So if we remember going back to our naming, this is called an isobutyl. So dibal is diisobutyl aluminum hydride. Yeah, this one's really bulky. It will only add in one equivalent of hydride very controllably. To be perfectly honest, I'm not sure why they don't use the lithium terbutoxy aluminum hydride, but I don't believe it works well. So this is a useful workaround.
Is there true that this doesn't work well with the reaction to lithium terbutoxy?
Yeah, this one's almost exclusively used to convert esters into aldehydes, at least in the Klein textbook. All right, the last reaction is with Grignards. So let's say we take our ester. I'll just use methyl ester. And we slam this with Grignard reagents. Will the Grignard reagent add in once or multiple times? Multiple times. It's really hard to control it adding in only once. We'll quench this with water, and we can use this to form our tertiary alcohol. Not super exciting, but synthetically useful. Does that make sense? Do you guys want to make a reaction map with esters? Or do you guys want to do synthesis problems?
Reaction map.
Oh, man. Raise your hand if you want to do some synthesis problems. A couple people, reaction map? All right, let's do a reaction map, and then if we have some time, we'll try to do some synthesis practice. I think reaction maps are useful just for reviewing all of the reactions, even though it feels really redundant and dry. So we've got our carboxylic acid, we've got our ester. We said we can convert our ester into a carboxylic acid. We can convert it into a primary alcohol. We can convert it into an aldehyde. we can convert it into a tertiary alcohol. And just for the heck of it, we'll put amides on there because you might see it pop up occasionally. So let's try to come up with 3 different ways that we can make our ester. What's one way? Anybody want to throw out a suggestion? Think. What's that? Alcohol and acid, right? So we'll use catalytic acid, methanol. We'll remove water from the reaction. We could use a Dean-Stark trap to favor that. The other one we saw was just go old school, SN2, deprotonate, react this with methyl iodide. That could work. The other option, if we want to get fancy, is to convert it to an acid halide first, and then react it with methanol and pyridine. So either of those 3 routes could work. And then if we want to convert this to a carboxylic acid, we had 2 different ways. One way we said was under acidic conditions. So we could just use H3O plus dilute. All right, so acid catalyzed hydration. The other way was our saponification, where we treat this with sodium hydroxide, followed by an acidic workup. And then for reduction, what do we need? Yeah, LAH. So lithium aluminum hydride. We need this in excess, followed by a water workup. And then if we want to convert it to an aldehyde, we said we need a bulkier hydride source. That was our dibol H, right? Followed by a water workup. And then if we want to convert this to a tertiary alcohol, Grignards with excess, followed by a water workup. And then for this one, I'll kind of do it as a dotted arrow because it's crummy. We could just use NH3 excess. However, like we said, that's a pretty poor reaction.
Well, would you like get us to be in that problem, or?
I'd be like more disappointed than angry. All right. So yesterday, I challenged you guys to come up with a synthetic route for ibuprofen. How many of you guys actually did that? One person? All right. I'm not going to lie, that's kind of what I was expecting. Propose a synthesis of ibuprofen. This could be one that I could give you on an exam. But let's try to figure out how we can make ibuprofen from this. Or from benzene and building blocks with 4 carbons or fewer. So I'll give you guys a little bit of time to work on this, but pay attention to old chemistry and new chemistry. This isn't an immediately apparent solution. So I'll give you guys a chunk of time to work on this. Let me pause the recording though. All right, so for this one, you can use benzene and alcohols or carboxylic acids with 4 or fewer carbons, just to clarify. All right, so you can use benzene, alcohols, or carboxylic acids with 4 or fewer carbons and or CO2. I'll clarify that. CO2, you can think of it as being a carboxylic acid derivative.
Yeah. Turning benzene into aldehydes. Benzene into aldehydes. Because this is not aldehyde.
Yeah, I mean, this isn't going to be activated, but I would say try to get this here on first. All right, let's try to come up with half of the synthesis together. For the first part, let's propose a way to get this isobutyl group on there. How can we get that on there?
AlCl3.
But do we want to do a Friedel-Crafts alkylation? An acylation? Oh yeah, if we do the Friedel-Crafts alkylation, if you think about it, this carbon right here is primary. It would rearrange. Remember with Friedel-Crafts alkylation, you go through a carbocation, and that can quickly rearrange. So in this case, we might have to have a workaround of Friedel-Crafts acylation. So let's make our carboxylic acid with 4 carbons or fewer. How can we turn this into an acid chloride? Thionyl chloride. Okay, and then we've got benzene and aluminum trichloride. Okay, now we're almost there. We've got our acylation. How can we get rid of that carbonyl? Rainy nickel sulfur. All right. Yeah, let's do the Clemenson reduction. All right, now if we think about this, we've got this alkyl group on there. Do you think the ortho position is going to be very available for attack? No, it's sterically blocked. So now we've activated this paracarbon. So now the question becomes, how do we append the rest of our molecule on there? Like that.
Friedel-Crafts now.
Yeah, let's do another Friedel-Crafts. So I'll show you guys kind of what I was thinking, at least. There's not one right way. So we've got another acyl group on there. But we need to pop on some other groups on there. We need to add on a carbon where that oxygen used to be, and that needs to be a carboxylic acid. Does anybody have a clever way to get there? Not quite. So a Wittig would give you a carbon-carbon double bond. But I'll show you guys one thing I was kind of thinking about was we could reduce this, right, to form an alcohol. And methanol. This could give us our racemic alcohol, right? Then, how could we turn that alcohol into a bromine? PBr3, or in this case, we could just use HBr, right? Because it's a benzoic carbon, so I'll just use HBr. Now we're getting really close. How can we get the last carboxylic acid group on there? Why is my pen not working? So we've got bromine right here. How can we go from here all the way to our ibuprofen product? Anybody have a proposal?
Do we make it into ketone? Again.
Not quite. The big thing we need to consider is we need to get this carbon installed. Yeah, Grignard, right? So first step, we can throw in magnesium metal. And then what can we add the Grignard into to get one carbon attached? What was that? Think about it this way, right? This is now going to be our nucleophile, and we're adding this whole group in. CO2, right? We saw we can make carboxylic acids from CO2. So in this case, we can make this into a Grignard, react it with CO2, and we can quench it with H3O plus in order to get our final carboxylic acid. The reality is in industry they do this way more efficiently, but they're using organometallic reactions that we haven't learned. But I thought this was a nice practice problem to go over old chemistry. All right, have a good weekend, you guys. I'll see you on Monday.